Take a look at this argument. If it is snowing, then the mail will be late. The mail will be late, therefore it is snowing. You might remember this argument from an earlier thought primer in which we were constructing ordinary truth tables using L equals 2 to the n to determine all the possible true-false values for the component parts of the argument and to determine whether or not it was in any way possible for the conclusion of the argument to be false when all of the premises were true, right? That's what we're looking for when we look at validity. Is it even possible for the conclusion to be false when the premises are all true? If so, that's an invalid, unreliable argument. If not, then it's a valid argument. It's a reliable argument. Now, we're going to test this argument again for validity, but we're not going to use an ordinary truth table. We're not going to use L equals 2 to the n. We're going to use a different kind of truth table called an indirect truth table. And I think you're going to like it because they're kind of fun, okay? So an indirect truth table is still going to reveal whether it's possible for the conclusion to be false when the premises are true, but it's going to do it in a much more efficient way. So if you're tired of drawing lines, you're going to really like indirect truth tables. So here's how indirect truth tables work. We're going to determine the validity of an argument by determining if it's possible for the conclusion to be false when the premises are all true. And we're going to do that by just assuming the main operator of the conclusion is false and the main operators of all of our premises are true. Okay, so we're just going to assume the conclusion is false and all the premises are true. And then what we're going to do is we're going to determine logically necessary truth values based on those beginning assumptions. And if we can determine all of the logically necessary truth values without running into any contradiction, without breaking the rule of horseshoes, or without asking a single statement to be both true and false at the same time, then we will have proven this argument is invalid. We will have shown how. We will have shown what combinations of true-false values allow this argument to have a false conclusion even when the premises are true. But if we run into problems when we're deducing these truth values, because we run into a contradiction, we're asking a particular statement to be both true and false at the same time, or we're breaking the rule of triple bars, then that means we've shown it's impossible for this argument to have a false conclusion while the premises are true. Okay, so I know this is all in the abstract, so I'm going to show you exactly how we roll. Okay, so we have our argument, and our first step is the same as it was when we were using ordinary truth tables, and that is to assign the simple statements that comprise the argument individual letters, and then represent the argument on a single line using those letters and our operators. So if it is snowing, the mail will be late is our first premise. The second premise is the mail will be late, and the conclusion is it is snowing. We've marked our premise, we've separated our two premise statements with a single slash, and we've separated our conclusion from the final premise with a double slash. Okay, so now what we're going to do is we're just going to assume that conclusion statement is false, and we're going to assume all of our premises are true. Okay, so we're just rolling from this assumption. Premises are all true, conclusion is false. And now we look at our truth table, or not truth table, we look at our argument, our symbolized argument, and we say, okay, is there anything else I can know given these assumptions? And we could say to ourselves, well, yeah, one thing I know is this: if L is true here, as I'm assuming it to be, then L would also have to be true here, because this line represents one moment in time, and L can't be both true and false at the same time. Similarly, if S is false here in the conclusion, it's got to be false up here in this premise. And I just figured out all of the logically necessary truth values for this argument without running into any contradiction. And now I can see that my first premise is reflected here by line number 3. And that retains the truth value of this horseshoe here. So what we've just done is we've proven it is possible for the conclusion of this argument to be false even when the premises are true. We did this in our previous thought primer when we constructed an ordinary truth table. And you can see in our ordinary truth table, line 3 looks exactly like this. Okay, so we assumed the conclusion was false, all of our premises were true, we deduced all of the logically necessary truth values we could, never running into a contradiction. And it's when we don't run into a contradiction that we've now created proof that this argument is invalid. We've shown how it's possible for the conclusion to be false even when the premises are true. So there's kind of an odd thing going on here where we were successful at deducing all of the truth values, so it feels like yippee. But really, it's like, oh, bummer, this is an unreliable argument because I was able to complete this task successfully. All right, so in the next lecture, we'll look at an argument where we're not able to deduce all of those logically necessary truth values without contradiction.